Hi, my name is Anirudh, and today I will be introducing the concept of power of a point. This theorem deals with lines that pass through circles and intersect at a given point. Shown here are the possibilities of this intersection, with the point being inside the circle in the left example, and the point being outside the circle on the right. Looking at the left example first, we can see that there are four segments touching the intersection point. We have PA, PB, PC, and PD. What power of a point tells us is that the product of PA and PB is equal to the product of PC and PD, as shown above in this equation. And this works for any two lines that intersect at a point inside a circle. Turning to the case on the right, the theorem states the exact same thing. The four segments with the intersection point are still PA, PB, PC, and PD. So the same concept applies. A special case depicted here is with the tangent line, PE here, which can be thought of as the same line, just repeated twice. Therefore, the product in this case would be PE times PE, which would be PE squared. And that's the third part of this equation at the top. A good way to make sure that you have the theorem correct is to check that all four segments in your equation contain the intersection point. So in this case, we have P as our intersection point, and in all four segments in this equation, we have P as one of the endpoints. Now let's try a problem. Rectangles ABCD and EFGH are drawn such that DECF are collinear. Also, ADHG all lie on a circle. If BC equals 16, AB equals 107, FG equals 17, and EF equals 184, what is the length of CE? Pause the video here and try the problem on your own. Now let's solve the problem. Well, we know CD, which is given by AB equal to 107. So if we knew DE, we'd be done. We can imagine the circle that's referred to in the problem as passing through A, D, and H, and it continues on to pass through G at some point. And by drawing it, we might think of using power of a point because we have a circle and we're looking for lengths. But which point do we choose to take the power of? Nothing inside the circle looks to be a good candidate, so let's look outside. In particular, if we extend GH past H and AD past D, we get an intersection point right here. Let's call it P. We have PH equal to DE because we formed a rectangle. PG is equal to PH plus HG. And with the given information, we have HG is equal to EF, which is 184. And PH, like we just said, is the same as DE. So we can write this as DE plus 184. And if we look at the other side now, we can see that PD equals it's the same as FG, so it's 17. And lastly, we have PA is equal to the sum of PD and DA, which are both given lengths in the problem. So that's equal to 16 plus 17 equal to 33. Now let's say we take the power of point P with respect to our given circle. So as we saw before, we need P to be in all four segments that we use. So let's write PH times PG is equal to PD times PA. Now if we substitute in our values that we just went over, we get that PH, which is DE, times PG, which we know is DE plus 184, is equal to PD, which is 17, and PA, which is 33. Now if we were to evaluate 17 times 33, it's 561. And from here, it's pretty straightforward what we have to do. We get a quadratic that we can rearrange to become DE squared plus 184 DE minus 561 equals 0. And from here, you just have to try a few values, some factors of 561. And after doing that, we get DE minus 3 times DE plus 187 equals 0. And since DE is a length, it has to be positive, which means that DE is equal to 3. Now if we go back to the problem, that's not what we want as our final answer. We're looking for CE, which is CD minus DE. So our final step in this case would be CD minus DE, which we get to be 107 minus 3, and we get 104 as our final answer. Thank you.